Alrighty, let's get started. So hopefully my voice sounds a lot better. I'm using a stand mic. Probably start streaming on Twitch now. Quit my job and hopefully gain success in there. Anyways, without further ado, let's get into it. So, lab number 4. You guys essentially were dropping ball bearings into a column of glycerin. It was probably one of the fastest labs you ever had in your life. Why does it matter? Well, I can tell you right now that lab kind of hints or previews an extremely complicated field in fluid dynamics, namely aerodynamics, or basically any fluid that travels faster than laminar flow, right? How do we know if something is laminar flow? How do we know if something is turbulent flow? What do those terms even mean, especially when it's going around a body? Well, first things first, we should probably define this term right here. It's called the Reynolds number. Reynolds number is super important. Probably, arguably, one of the most important dimensionless parameters you'll see in undergrad. You'll notice here that it can fit for different sizes of different shapes. So characteristic length and characteristic speed. That could be anything from, like, I don't know, the length of if you have a cube, it'll be the side of the square, or the diameter of a sphere, or name some kind of important distance. And then its speed, right? So this could be the airspeed far away from the body. Could be terminal velocity that the object travels at. Could be any one of those terms. Something important here, dynamic viscosity is specific to certain fluids, and then kinematic viscosity is just the dynamic viscosity of your fluid divided by the density of that fluid. These are denoted by mu and nu, respectively. So you will see that everywhere. Also, I don't know how sensitive this mic is. You might hear my dog in the background whining for attention, but unfortunately, she has to learn that I can't always pay attention to her. So, anyways, so why is this important? Why do we care about this dimensionless property? Well, you can see here we have a sphere with fluid going around it. So we can see when this number is very small, so it could be that the speed of which this ball is moving at, or the air is moving around it, is going extremely slowly. Or maybe it's extremely tiny. Or maybe we're moving through a very viscous solution like honey or something like that. The main thing that you have to worry about is skin friction, right? So the fluid is rubbing up against the surface, and then the fluid has to then interact with itself. That's where you're going to get most of your losses. But we see as Reynolds number starts to increase, we see that the entire flow starts to change shape, right? Also, if you want to know something interesting, there's something called, I think it's called like von Karman streets. Yeah, there's how you spell it. It's a really cool GIF. Anyway, sorry for getting distracted. But you'll see that you now have to start worrying about things of like, okay, well, what does the air do after it leaves the body? So, for instance, like when you are moving at pretty considerable speeds, or you're a larger body like a car, you're now worried about the pressure wake behind you. That's where you're going to get most of your drag, most of your energy losses, is the air essentially having to be shoved around you and then fill in the gap behind you, right? So how do we figure out that drag force? Well, once you start getting into the turbulent regime, or basically anything outside of creeping flow, and creeping flow, by the way, is just when Reynolds number is very small, we have a term for it where it's, I think the best way to describe this is semi-empirical. So it's kind of based in theory. but mostly you figure this out through experiments, namely this CD term. We call this our drag coefficient. Hint, hint for the lab. Essentially, you run some experiments, figure out what the drag force is for a body moving at some certain speed with some frontal area. So this frontal area is essentially the projection of whatever body is into the fluid. So in this case, you have a sphere, it becomes a circle. And you have all of these numbers, and you're just left with CD, right? The problem is this drag coefficient is heavily related to the Reynolds number, which you can see here depends on a few terms. And it's nonlinear. In fact, it's heavily nonlinear. Here is a ball of different like roughnesses, right? So maybe it is grooved, or maybe it's dimpled. It's something. And you can see here on the y-axis, it's the drag coefficient. And then on the x-axis, it's the Reynolds number, right? So you can see that there's like this sweet spot for a certain size and a certain speed of a certain fluid, and let's just claim it's air for now. You minimize the drag coefficient, which means then you minimize the drag force experience. So if you're an engineer, you can design the the roughness of a ball, right? If you know exactly what speed you're going to go at to minimize the drag. Or if you play sports and you have a certain size ball that you know humans can only hit so hard, so meaning it'll only go so fast, you can groove it or dimple it such that you can minimize the drag coefficient. And comparing the smooth ball, you can see that the drag coefficient is way better. In fact, it's almost half of what the smooth ball is. But say you're wanting to now shoot that ball out of a, cannon, you could see that if you try using the golf ball or any of these that are rough, well, you're going to have a lot of losses now. It's better to be the smooth ball, right? In fact, this is pretty near and dear to my heart because my senior design essentially, here's me as a little baby. We were going to make a full shell for this vehicle, and we were asking ourselves, okay, well, if we had just the shell, that's kind of boring. I saw this thing on Mythbusters where they're like, what if we dimpled a car, and it actually made the aerodynamics a lot better? First off, I want to know why, but then also, can we do that? And as you can see here, here's like a blunt body. You have these metal protruding bars. Here's our body. Here's the big wheel in front. I should have modeled the two wheels in front, but due to time constraints, I didn't. And you can see like we have this large pressure wake, right? But if you use something a lot more aerodynamic, it's a lot more streamlined. This pressure field is a lot smaller. And we also investigated like what happens if we dimpled it, right? What if we textured the surface? Or what if we put these things called vortex generators, where you purposely make the air more turbulent such that it delays this pressure it's called flow separation. It delays that, so this wake is a lot smaller. And we find that here is just the bare frame. Here's if we did nothing at all, and we can still lower this drag coefficient by dimpling it. And then I think we did extra trials where we put vortex generators on the underside, right? So we even lowered it further. So small enhancements. I mean, if you're racing a bike, you're probably not going to see much of an advantage, but we did some quick math, and we actually found that as you start to really pick up speed, you want having the final shell, you could see that there is a large difference in the force experience, and same thing, power lost. There's my entire 4 years of undergrad summed up in probably 5 minutes. So that existential crisis aside, let's go back to doing the lab, the real reason why you're watching this video. So this is some data given to me by two students. Those two students, thank you kindly. It's a lot of numbers, don't worry about it. You guys will remember that you calculated information specifically for multiple bearings of a certain size. You had like 3 trials per each size. You're essentially, what you're going to do, and this is what I highly recommend you do, make another table where you're going to take the average of those 3 trials, right? So for the .0625, I think that's 20 gauge bearings, just averaged it out, and that's what you get, right? So where do all these values come from? Well, you have the diameter, make sure you convert that to meters, and then you'll have your weight in newtons. So this is just the volume of your bearing, the density of steel, which is given in your lab manual, times gravity, it's weight, mass times g. Fluid density, this is something I gave you in the lab. It's 1260 kilograms per meters cubed. This is the density for pure glycerin. I have a feeling it's actually cut with water, or maybe it just became less viscous over time. But for now, we're just going to assume this density so you guys can actually, do the lab, because I don't want you guys reaching in and doing density measurements. Way too messy. We have the length. It was those 2 points you measured. I think it was 24 inches. And then your terminal velocity was just the length divided by the time it took, the average time it took. How do we get this terminal velocity? Well, that terminal velocity happens when there is a balance between the weight and the drag force and buoyant force. Well, what is the buoyant force? The buoyant force is simply you can think of it like the anti-weight of the fluid displaced. So the volume of the fluid displaced is, again, same thing for the ball bearing, times the mass, or the density of glycerin, which we are just going to assume is 1260 times g. Great. Then your experimental drag. Okay, this is where things start to get a little bit interesting. So your experimental drag is just weight minus the buoyant force, right? That's the only 2 things that could be that bearing could be experiencing. So we at least are pretty certain that this is a real quantity, right? This is where, by the way, when I say semi-empirical, you're going to see why I say that in just a few moments. But another term we need is the dynamic viscosity. Okay, how do you find the dynamic viscosity? The dynamic viscosity, you can use equation number 3. Now, equation number 3 can only happen when you have extremely slow speeds, or you have something we call creeping flow, and that's when the Reynolds number is very small. So here's a fun word for you. A priori, we knew that we had creeping flow because we had a very small bearing, so D was small, right here, and it was moving extremely slowly. If you look at U, very tiny. So that we could probably guess that whatever this value is going to be, it's going to make the Reynolds number very small. So we were justified using equation 3 to solve for the viscosity. How do we solve for the viscosity? Well, you have your experimental drag force, set that equal to this equation number 3, and just rearrange to solve for mu. And that will be your average viscosity, okay? So, how do we find your drag coefficient? Well, once again, you have your experimental drag. All you're going to do is rearrange this equation, your semi-empirical equation, to solve for your drag force, right? And that's it. That your drag force, or your drag coefficient, is an empirical, it's an empirical quantity that you just get from doing experiments over and over and over again, right? I would recommend, if you want to get fancy, if you want to put like this line here, this theoretical line, make a column. I called it equation 3A. If you look in your lab manual, we go right here. This is where I got that equation from. It is essentially assuming Stokes flow So Stokes flow or creeping flow is when Reynolds number is much less than 1, and you can use this equation. Essentially, a lot of math happens, but you can relate the drag force, the coefficient of drag to the Reynolds number through a very simple equation, 24 divided by the Reynolds number. Okay. You don't have to do this one. In fact, here, you know what? There, it's grayed out. You don't have to do this, but I just put it there for illustration. Okay. So then we calculate the Reynolds number. All the Reynolds number is just the density of the fluid times its speed, u, times its diameter. Make sure you're using meters, the converted one, not inches. You'll get something incorrect. And then the dynamic viscosity. Here's a tip for a lot of people. Instead of going in and trying to constantly reassign this value, if you look here, if you put these dollar signs there, it locks in that that value. So for example, like if I try click and dragging this all the way down, like I get garbage. It doesn't work. But if I go here and then put dollar signs in front of the column and row, so the letter and number, and now I click and drag, you can see that it just freezes that value for every single one. So that's kind of neat. Okay. Then what you're going to do is, one of the questions that it asked you is basically how wrong is it to use the creeping flow drag for when the Reynolds number is not much less than 1. So what you're essentially going to do, you can see here the columns are you're just using this equation for the given speeds and diameters. Okay. Here's a really good way to visualize that. I just did a percent error. Percent error in this case is the absolute, so ABS, abs, just the difference between your experimental drag force and then this drag force that is predicted by equation 3. Divide that by equation 3's drag force, multiply it by 100, bring it all down, and you get all these percent errors. What I would recommend you guys doing is making this graph right here. Essentially, this is bar graph, and you know what? Just to show you guys how to do it, I will demonstrate that. So we will do this. I go up here, make a 2D column, right? It's blank, nothing selected. I'm going to select my data, add, and then, thanks. Go through my percent errors, select them all, and now here is something kind of neat. If I edit that horizontal range of values and I try selecting all these diameters, it will let me do that, right? Hit OK. It will let me do that, but you can see that I had 2.1875s, right? So I want to denote which one is the rough bearing, and you can't just put like an R right here, because otherwise, you know, it just gives you null values everywhere. So one thing you can do, and this is what I recommend, Control C, so copy this entire column, and here's another little tip. You want to right click, and instead of just pasting the values, what you can do is, pasting the cells, which will also, thanks for asked, post like the equations used, just post the values. Now when you post just the values, it won't copy all the different equations. So this is like really helpful if, like, say, you know, if I tried to control this, well, you know, I only want the values. So you could change that to just pasting the values instead of just having to retype it in. Really, really helpful. So yeah, so that's all well and good. So now if I go here, chart design, select data, edit that row again, go here, select all of these. Now I can see that those R's means rough, right? So that's really nice. And this is a really good way of visualizing your data. Speaking of visualizing data, you actually plotted the drag coefficient to Reynolds number for the rough ball bearing. And I did that exactly here. I also plotted equation 3A. So this is if the creeping flow drag was continued to be plotted. Oh, you guys probably should learn how to do log-log plotting. So you know what? I'm going to make this equation or this graph from scratch. So let me just make a new equation. What I'd recommend, if you're going to plot also this theoretical, do this one. If not, don't worry about it. But so I'm going to select my data. On the x-axis, I want my Reynolds number. So remember, all these values are the smooth values, so I'm just going to call this experimental smooth. And then my y values are going to be the drag coefficients. Right? Cool. And then we have our experimental rough, and that are just these values. There we go. And then we have our theory equation 3A. And for those values, we'll just do the smooth ones. We'll just plot that. Okay, so if we look at our graph, it means absolutely nothing to us. We can't really make heads or tails of it. So one thing that we do is we do a log-log plot. So we take the logarithm of the x-axis and the logarithm of the y-axis. Okay, so you double-click the x-axis and go here to logarithmic scale. And again, you double-click the y-axis and do logarithmic scale. Now, what we could do, quick layout, real nice, and then I already showed you how to do this, but in case you guys forgot, just double-click here to pull up this format chart, so in case that didn't show up, just double-click somewhere in the chart, click, this will be my theoretical lines, so I don't want any markers. Oops. Here we go. And then for my experimental, I don't want any lines. No lines. So yeah, so there you go. Okay. If you want to make it look a little bit more fancy, you can add, I don't know, like some minor grid lines. And this will actually highlight the importance of using a log-log chart. So you can see here, you know, here's 1, and then, or I'm sorry, we'll use 1, 2, 3, 4, 5, 6. It gets very small until you reach 10, right? So that's how you essentially do that. Okay. So there's a reason why I have two students graphs, because this kind of confused me. This experimental for the rough beads, I wanted to know if this was a fluke or not. And looking at it, I can see that we have one that dips below the experimental smooth and one that goes a little bit above. So I kind of thought to myself, well, if we look at something like this, we could see that it's better to be rough until later when you start increasing your Reynolds number, and then it's better to be smooth. So I think what's probably happening is I took the graph and kind of just sketched it. This kind of looks like the general trend for the smooth bearings, and this kind of looks like the general trend of the rough bearings. Now granted, I only had 2 data points, but I was trying to make sense of it. So this is kind of like my prediction So one of the questions, I think, in further discussion, where is it? Yeah, so plot the coefficient of drag to the Reynolds number. There is one of the questions that asks, like, oh, here you go. Does roughness have an effect on drag? Compare with values and explain any differences, right? So, I mean, yeah, you could show it. It's you can't just say, the rougher, the worse it off, or the worse the drag coefficient is, because, well, when you have something like this, it's highly nonlinear. It's kind of hard to predict things. So I will leave that to your discretion. I'm purposely leaving that open-ended because I want to hear your guys' thoughts, make some educated guesses. Also, you guys might have seen in your lab manual this chart right here. Interesting thing is this could be any kind of sphere moving through any kind of Newtonian fluid. So air, water, most honeys. So I just did a quick overlay of the graph, and I know this is an eyesore, but here's our experimental data, and you can see it kind of follows this curve. So you don't have to do this. I just thought it was interesting to actually have it all line up, map out like that. So there is that. Oh, I wanted to quickly go through the further discussion questions, because there are some pretty hard questions to answer, right? So why do you think we use data for the smallest sphere? You better answer with the Reynolds number, so help me. It's literally a chief condition. If you release the spheres close to the cylinder's wall, would you expect the same results? This is actually a pretty involved question, and it's something you can use the theory from Lab 3 to answer. So I made this sketch, and I'll walk you guys through it. So let's say there is this ball. This ball is falling through the fluid, so it's traveling this way, and it's traveling close to the wall. So fluid is going to, move around it like this, right? And it starts to peter out, and then once you get way out here, we assume that it's flat. What gets interesting is right here. If you guys remember the Venturi effect, so think of this kind of like a weird shaped tube, right? So imagine you had a tube. So here's kind of like the cross section, right? And it goes, kind of looks like this. So right at 2, you have your choke right here. It's kind of like a bottle, and then it opens up. Or maybe we're like an hourglass, maybe, right? So you'll notice that the area then constricts. Well, you still have fluid that must go through here, so let's just call this Q ball right, and then the flow rate ball to the left, okay? So you'll notice since the area constricts, the velocity increases, and because the velocity increased, the pressure decreased when you go to 2, right? So if we look at the flow rate on the left-hand side, well, the velocity, the area stays roughly the same, right? Maybe it changes a little bit. For the most part, though, we will assume that the area from 3 to 4 is roughly the same. Because if you think about it, this is a large tube, a very large tube. So technically, if we're looking at the area, like the diameter from here to here, D3 is basically the diameter of D4, right? So that we're pretty justified in saying that the area of 3 and area of 4 are basically the same. So that means the velocities at these points are basically the same. So the pressures at these points are basically the same. So P1 and P3, we'll say they're roughly the same because they're at the same level, right? This is before the ball interacts with the fluid. So P1 and P3 will have similar pressures. P3 and P4, we again stated that those pressures are the same. P1 is greater than P2, so P1 is related to P4, so that means the pressure at 4 is greater than P2. Well, here's the problem. You have a delta P scenario, so you go from highest pressure to lowest pressure. You're actually going to push this ball against the wall. It's going to actually hit the wall and start rolling on this wall. And of course, that will affect your measurements. So this is actually a really involved question. It's a very interesting question, but I thought you guys should be aware of how to answer it, right? So just, explain all of this in words. Easy peasy. What do you conclude from the shape of the CD curve? Okay, this is how I want you guys to answer this. Don't just say, I can't make heads or tails of it. I don't know what to think of it, okay? There's a reason why I plotted equation number 3, right? Equation number 3 is for creeping flow. See how the points start to deviate away from the creeping flow? Please, I am begging you, when you are writing your conclusion and discussion answers, talk about how it deviates the faster you get, because you're violating this condition worse and worse and worse. Okay, so that's how you answer that question. Why is this graph that we made, why do we do it on a log-log scale? You know what? Because it's funny, you can get smart with me. For this one, if you really wanted to, if you wanted to plot this, literally just show me the plot. What does that look like when you don't do it? Okay, here is the plot. It's very hard to glean any information, right, when there is no log-log plot, right? Because if you think about it, from 0 to 1, the drag coefficient changes immensely. And then from 2 to 200, the drag coefficient might not change that much. So there's a reason why we use log-log plots. It's very, very, very helpful in trying to plot anything that obeys some kind of exponent or power law. So technically, if you see this, if you do a log-log plot, so here's a little neat trick. When you end up taking the logarithm of CD, specifically, there's going to be a bunch of math that happens. So I'm actually going to do the natural log. You can turn off your brain, by the way, if this confuses you. Just ignore me for this part. Natural log of 24. You will find sorry. 1 minus Reynolds number plus 24. Essentially, this is the long-winded way of saying the reason why you do log-log plots is that this kind of looks like y equals mx plus b. Here we see something that has a power law. If you're really interested, I can explain this more in person to you. But just so you know, the log-log plots, you could see that spread of data. You wouldn't be able to see anything interesting. It's all going to bunch up when the Reynolds number is less than 1, and then when Reynolds number is greater than 1, from 1 to say, we have Reynolds numbers that can go to a few billion. It's going to be really hard to see any kind of meaningful change in your drag coefficients. And this is all about visualizing your data. All right. I think that's everything I have to say. That was super long-winded. Sorry if I rambled or just kind of spaced out. Hopefully I didn't. It's currently midnight right now. I wanted to get this out to you guys as soon as possible. So yeah, let me know if you have any questions. Let me know if the audio came through very decently. And I think that's everything I have for you guys. So, I will see you guys next time. Goodbye!